In this lesson, we're going to look at graphing systems of equations. You'll learn how to determine whether a system of linear equations has 0, 1, or infinitely many solutions, and solve systems of equations by graphing. How can you use graphs to compare the sales of two products? During the 1990s, sales of cassette singles decreased and sales of CD singles increased. Assume that the sales of these singles were linear functions. If X represents the number of years since 1991 and Y represents the sales in millions of dollars, the following equations represent the sales of these singles. Cassette singles, Y equals 69 minus 6.9X. CD singles, Y equals 5.7 plus 6.3X. These equations are graphed at the right. The point at which the two graphs intersect represents the time at which the sales of cassette singles equaled the sales of CD singles. The ordered pair of this point is the solution of both equations. When I calculated it out, it came out at 4.8 and 35.9. So that ordered pair is the solution of both equations. The intersection where they cross. Two equations such as y equals 69 minus 6.9x and y equals 5.7 plus 6.3x together are called a system of equations. A solution of a system of equations is an ordered pair of numbers that satisfies both equations. In this case, it was 4.8, 35.9. The system of two linear equations can have 0, 1, as in this case, or an infinite number of solutions. If the graphs intersect or coincide, the system of equations is said to be consistent. That is, it has at least one ordered pair that satisfies both equations. If the graphs are parallel, the system of equations is said to be inconsistent. There are no ordered pairs that satisfy both equations. Consistent equations can be independent or dependent. If a system has exactly one solution, it's independent. If the system has an infinite number of solutions, it's dependent. If it makes sense to you to write down all the words that I just read to you, you can, but I like the chart here. It summarizes everything we just said verbally. If the two lines intersect, there will be exactly one solution. It's consistent and independent. If the two graphs lie on top of each other, there are an infinite number of solutions. It's considered consistent and dependent. Parallel lines, by definition, don't cross. There are no solutions, and it is inconsistent. Use the graph to determine whether the system has no solution, one solution, or infinite many solutions. They are parallel lines. They do not cross. There is no solution. This one, we can see where they cross. They cross at 2, -1, so that is one solution. These two lines lie on top of each other, so if a point is on one line, it's on both of them, so that is our, oops, I was trying to circle that, infinitely many solutions. I could write the infinity sign, but that's kind of sort of right. It should technically be somehow involving that equation because it has to be on the line. For our purposes, I think infinity is okay. Okay, this is another example of the same thing, and this is kind of how they do it in the book by putting a whole bunch on the same graph, so I wanted to look at it too. If we want to look at 2y plus 3x, not a great line, but just showing you where it is, and y equals x minus 1, they cross, so that's going to be one solution. Y equals x plus 4 and y equals x minus 1 are parallel lines, so that is no solution. And when we went looking for y equals -3/2 plus x plus 3, we found out that we'd already graphed that one once, so that's going to be our infinitely many. Graph the system of equations and determine whether the system has no solution, one solution, or infinitely many solutions. If the system has one solution, name it. Okay, so to graph, we like to solve for y. First, put it in slope-intercept form because it's nice. So I have -y equals -3 minus 2x divided by -1. So y equals 3 plus 2x. And then my other equation, 8x minus 4y equals -12. Subtract 8x. So negative 4y equals negative 12 minus 8x. Divide both sides by negative 4. So y equals 3 plus 2x. That looks familiar. So yeah, when we solve for y, we got the same exact equation. So this is our infinitely many. They are dependent equations. One depends on the other. They are the same line. Okay, again, let's go ahead and solve both sides, both equations for y. So I have negative 2y equals 4 minus x. So divide by negative 2y equals negative 2. Negative divided by negative is a positive, so plus 1/2 x. And then the second equation looks very similar. So I'm going to subtract x from both sides. So negative 2y equals negative 2 minus x. Divide both sides by negative 2. And y equals 1 plus 1/2 x. Okay, they both have the same slope. They have different y-intercepts. Lines with the same slope and different y-intercepts are called parallel. Therefore, they do not cross. So that's going to be our no solution because they are inconsistent. Okay, I need to complete this. They gave us 3 possibilities, and so far we've done infinitely many no solution. Let's do one where they cross. So these two cross at the ordered pair. What would that be? 0, 3. So this is our one solution. And it's at 0, 3 because I went over 0, up 3, and it works for both lines. Tyler and Pearl went on a 20-kilometer bike ride that lasted 3 hours. Because there were many steep hills on the bike ride, they had to walk for most of the trip. Wouldn't we call that a walk instead of a bike ride? All right. Their walking speed was 4 kilometers per hour. Their riding speed was 12 kilometers per hour. How much time did they spend walking? So far we have information about the time they spent riding and walking. We also know the rates and the total distance traveled. Let r equal the number of hours they rode and w the number of hours they walked. And we're going to write a system of equations to represent the situation. Yes, the number of hours riding plus the number of hours walking was a total of 3 hours for the trip. And distance equals rate times time. So if they rode at 12 kilometers per hour, the distance riding would be 12r. And the distance walking would be 4, because they could walk at 4 kilometers per hour, W. And that equals the total distance of the trip was 20 kilometers. You know, this feels a little bit awkward because you're used to X and Y, but it still goes in alphabetical order. So my Y is my W now. So I'm going to subtract 12R from both sides. So 4W equals 20 minus 12R. Divide by 4. So W equals 5 minus 3R. Like the second equation. To solve for W, subtract R from both sides. So our blue equation started at 5, and it's going down 3 over 1, down 3 over 1. And our red equation started at 3, and it's going down 1 over 1. And they cross at 1, 2. And 1 was our time riding. And 2 was the number of hours spent walking. If we want to check, we can substitute back into our first equation. 1 hour for riding, 2 hours for walking, and 12 plus 8 is in fact 20. That's good. And if we just add 1 plus 2, we do in fact get 3. So we know it works in both equations. So 1, 2 is our solution. In summary, for graphing a system of linear equations, it can cross either once and be consistent and independent. It can lay on top of each other. There are an infinite number of solutions. It's consistent and dependent. Parallel lines do not cross. So there is no solution, and they are considered inconsistent.